Hello everyone, welcome to the part 2 of the series unit in AP Calculus BC. In this unit we looked at error to figure out how off we are from our actual answer, with the power series and Maclaurin and Taylor series, which is where we had variables in our series, other than n. So let's look at this first question. So for the convergent series, the sum of n equals 1 to infinity of negative 1 to the n plus 1 over 2n plus 5, notice that this is an alternating series, right? It's the negative 1 to the n plus 1. So when we're estimating the error, like we're asked to in part 1, we're going to be looking at the alternating series estimation theorem. So we want to estimate the error between the sum of the series and its 15th partial sum. And what this means, the 15th partial sum, what that means, that's just saying we're summing the series from n equals 1 to 15. So we're asked, how off is this from our actual value of the series? How off is this? So the way we're going to do that is by the alternating series estimation theorem, we're going to look at the n plus 1th term. So since we're looking at the first 15 terms, I want to look at the 16th term. And I know by the alternating series estimation theorem that my error is going to be less than the 16th term. So for 16, I'll just plug in 16 for n into my a sub n, into the stuff in the series. So that'll give me negative 1 to the 16 plus 1 over 2 times 16 plus 5, and we're going to put some absolute value signs on there. So if we evaluate this in a calculator, we will get 0.027. So basically, if you evaluated this finite series, this would be off of the actual value by less than 0.027. That's what this error actually means. So our error is less than 0.027. There we go. And then in part B of the question, we're asked, what is the lowest value n for which s sub n, the nth partial sum, is within 10 to the negative 5 of the sum of the series? So this time we want to figure out what value of n do I have to sum to in order for my error to be within 10 to the negative 5. So remember, we're looking at the n plus 1th term to get the error, right? So instead of n, I'm going to plug in n plus 1 into here. So it'll give me negative 1 to the n plus 2 over 2 times n plus 1 plus 5. And I want my error to be less than 1 over 50, so 1 over 100,000, right? I want to figure out what value of n will make my error less than this. You guys know we have to solve this for n. Okay, so if I simplify this a bit by getting rid of absolute values, I will get 1 over 2n plus 7, right? Simplifying this is less than 1 over 100,000. And then I can cross multiply. That'll give me 100,000 is less than 2n plus 7. And solving this for n gets me that n is greater than 49996.5. And then since n is an integer, it's like a number that we're plugging in, that we're summing to, n must therefore be equal to 49997, right? Because it's greater than that. So this is the number that if we were to sum to this, then our error would be within 10 to the negative 5, like we said, okay? So that was the first question. Let's move on to the second one. For the sum from n equals 1 to infinity of x to the n plus 2 divided by 2n plus 1 factorial, in part A, we're asked if x equals negative 1, estimate the sum of the series to within 10 to the negative 6, given that the sum converges. So we'll start by plugging in negative 1 in for x. That's going to give us the sum from n equals 1 to infinity of the stuff in our series. Plugging in negative 1 for x there, as you can see. Okay, so now we want to estimate the sum to within 10 to the negative 6. The way we're going to do that is we're going to be using the alternating series estimation theorem, because we have a negative 1 to the n plus an integer there. So what we're going to do is we're going to look at the n plus 1th term, like I said, in question 1. So we're going to be taking negative 1 to the n plus 3 over 2n plus 3 factorial, absolutely that, and we want that to be less than 10 to the negative 6, okay? So if we simplify this a bit by getting rid of the negative 1 because there is an absolute value, we'll have 1 over 2n plus 3 factorial is less than 10 to the negative 6. So now if I cross multiply, if it were, you will get that 2n plus 3 factorial, I should put parentheses there as well, is greater than 10 to the 6th. So 10 to the 6th, by the way, is a million. So I can just write a million there. And then, so the question is now, what value of n do I plug in here to get the 2n plus 3 factorial to be greater than a million? There's no like shortcut or anything. You just gotta plug in different values of n until you get one that works. So if you try n equals 3, for example, you'll get 9 factorial, and that's not enough. If you plug in n equals 4, you'll get 11 factorial. That is enough. 11 factorial is bigger than a million. So n equals 4 is the lowest value of n that satisfies this criteria, lowest integer value of n. So now, since n equals 4 satisfies this criteria, we're going to sum up all the terms before that. So we're going to be summing up the first 3 terms from n equals 1 to 3 of our stuff in the series. So the negative 1 to the n plus 1 over 2n plus 1 factorial. So this should estimate our sum to within a million. To within 1 over a million. So this is, if we plug in 1 into n, we'll get negative 1 squared over 3 factorial. And then we'll get, if we plug in n equals 2, we'll get negative 1 cubed over 5 factorial. And then we get negative 1 to the 4th over 7 factorial. Right, we're plugging in n equals 3 here. So if you evaluate this in your calculator, you will get, let's see here, you will get 0.158531746, and there's probably more characters than that, or more numbers than that, but this is the estimate of our sum to within 1 over a million. In part B, we're going a totally different route. We're going to find the center, interval of convergence, and radius of convergence of this series. Okay, so for the center, we're going to look at the x thing here. Remember how in the general form of a power series, the center is x minus a, where a is the center? In our case, we're not subtracting anything from x, it's x minus 0. So the center is at a equals 0. So the center is 0. So I'll write that down here, the center 0. And also preemptively write down the interval of convergence and the radius of convergence. I'll give us spots for those two as well. Okay, so now to find the interval and radius of convergence, we're going to be using the ratio test, which is the most common test for this sort of question. So we'll be taking the limit as n approaches infinity of the absolute value of the n plus 1th term divided by the nth term, right? So for this first one, I'll go slowly. We'll have, if I plug in n plus 1 into here, into n plus 2, that'll give me n plus 3. And then if I plug in n plus 1, I'll get 2 times n plus 1 plus 1. And then we're dividing by the nth term, so we'll be multiplying by its reciprocal. So 2n plus 1 factorial over x to the n plus 2. Okay. Now let's simplify this a bit. So we want it to cancel with the x to the n plus 2. So what I can do is I can use my laws of exponents to rewrite this as x to the 1 times x to the n plus 2. Right? This and this will combine to give me the x to the n plus 3. And then this will just give me 2n plus 3 factorial. And then here we'll still have 2n plus 1 factorial over x to the n plus 2. Okay, next step, we can mess with the factorial. So I want this to cancel with this. So I'm going to start listing the first few terms of this factorial. Okay, so we'll have x times x to the n plus 2. And so if I list the first few terms, first is going to be 2n plus 3. Remember, we're going to be listing decreasing terms, and we're going to be multiplying those until we get to 1. So it's going to be 2n plus 3, 2n plus 2, 2n plus 1, and so on and so forth. So 2n plus 1 and so on and so forth is 2n plus 1 factorial, right? And the reason I stopped at 2n plus 1 factorial is that it's going to cancel with this up here. There we go. So in an actual problem, you should be able to skip straight from this, not even from looking at the series, straight to this step, ideally. But since we're going through this slowly, well, I showed you every single step. Okay, so what was the point of doing all this manipulation? Well, look, this cancels, this cancels. So what does it leave us with? Well, it leaves us with the limit as n approaches infinity of x over 2n plus 3 times 2n plus 2. And what is this limit? Well, there's no n on the top, there's only the n on the bottom, so this limit is going to go to 0. And remember, for the ratio test to cause the series to converge, this step has to be less than 1. This limit has to be less than 1. And notice that no matter what the value of x is, it's going to be less than 1. So the value of x is pretty much irrelevant here, right? So no matter what x is, it's gonna converge. So that means our interval of convergence, that's basically what x values will cause the series to converge. Well, like we just said, it doesn't matter what the x values are, it's going to converge no matter what. So it can be literally anything. And therefore, our radius of convergence is also infinity, because it literally does not matter what the x value is. Okay? That was the end of question 2. Let's move on to the third one. Alright, so in question 3, we are fully in the power series world. We want to write a power series for the following 4 functions, and we have to identify either the interval or the radius of convergence using the fact that 1 over 1 minus x equals this sum for negative 1 is less than x is less than 1. So in these first 3 questions, we want to identify the interval of convergence, and for this last one, we want to identify the radius of convergence. So let's get started. For this first one, f of x equals 1 over 1 plus x cubed. Notice that this already looks very similar to 1 over 1 minus x. The only difference is that instead of a minus x, we have a plus x cubed. So I can actually rewrite f of x as 1 over 1 minus negative x cubed. And now it looks even more similar because just instead of this x, we have this negative x cubed. So that means here, I can replace this x with a negative x cubed, right? So for example, since this 1 over 1 minus x equals 1 plus x squared plus x cubed and so on and so forth, I can say that 1 over 1 minus negative x cubed equals 1 plus negative x cubed plus negative x cubed squared plus negative x cubed and so on. And if I wanted to write this as like a power series, I can say this is equal to the sum from n equals 0 to infinity of negative x to the 3 to the n, so negative x to the 3n by combining the exponents. Or I can just as equally write this as negative 1 to the n x to the 3n. So either of those work. I'm just going to circle this one, and that's that. So now we have to look at the interval of convergence. And now since we just replaced the x with the negative x cubed, our interval of convergence is not going to change from this one here. It's still going to be negative 1 to 1. So our interval of convergence will still be negative 1 to 1. So now looking at this one here on the top right, it does look a lot more complicated than our first one, but realize that it's basically still the same thing. We just have to do the same steps. So we wanted to get it to look as much like this as possible. So let's see what we can do. First, I'll bring the 3x squared out to the front. So we'll have a 1 on the top for a numerator. Like that. And then notice that I want to have a 1 here, so 1 minus something. So we can factor out the 5 as well. So we'll get 3x squared over 5 times 1 over 1 minus 2 over 5 times the cube root of x, right? So similarly, just like how last time we replaced the x with the negative x cubed, now we're replacing the x with the 2/5 cube root of x. Okay, and we're also going to multiply the whole thing by 3x squared over 5. So instead of, before we had the sum from n equals 0 to infinity of x to the n, now I'm going to replace my x with the 2/5 cube root of x, and I'm going to multiply the entire thing by 3x squared over 5. So my new series will be the sum from n equals 0 to infinity of 3x squared over 5, because we're multiplying the whole thing, and then we're going to replace the x with this, so we'll have 2 over 5 cube root of x. Oh, nope, that's not how we do. That is not how we do. The 3 goes here. The cube root of x, there we go, to the n power. Okay, and then that's my series. So for the interval of convergence now, it is going to change because of this, because this is like the 2/5 and that. So basically what's going to happen now is, since it's kind of like a geometric series, we want this stuff in here to be less than 1 for the series to converge. So we want -1 to be less than 2 over 5th cube root of x to be less than 1. The absolute value of this has to be less than 1. So now solving for x, we'll multiply first by 5/2 to get rid of this fraction. We'll get -5/2 is less than the cube root of x is less than 5/2. Now we can cube both sides, so we'll get -125 over 8 is less than x is less than positive 125 over 8. So our interval of convergence would be -125 over 8, comma 125 over 8. And we'll put parentheses to both these instead of brackets, because having it be 125 over 8 or -125 over 8 would cause the series to diverge, because the common ratio would be equal to 1 in that case. Okay, so that's our interval of convergence, and that is our series. Okay, so for this third part, we have f of x equals the derivative of 5x over 1 minus 3x to the 5th. Now, if you actually took the derivative of this expression and tried to find the power series of that, I am sorry for your loss. That must have been very, very difficult. Unfortunately for you, that was not the right way to go, because there's a much easier shortcut. So what we're going to do is we're going to take this stuff here and make it a power series first. So we'll define a new function, so g of x, that's equal to 5x over 1 minus 3x to the 5th. And we'll first just find the power series of this. So this is very simple, because it already looks similar to this 1 over 1 minus x, right? What we can do is we can say this is equal to 5x times 1 over 1 minus 3x to the 5th. I actually took the 5x and brought it down here. And now we already have it as 1 over 1 minus something. So we're going to replace the x with 3x to the 5th and multiply the whole series by 5x. So that'll get us the sum from n equals 0 to infinity. So we'll have 5x in the front, and then we'll have 3x to the 5th to the n. So this is, and because we are going to be taking the derivative of this in a moment, because we want the derivative, I'm going to rewrite this series a little bit to make our lives easier when we do take the derivative. So what I can do is I can combine, so I can distribute this n, so I'll get 3 to the n and x to the 5n. So what I can do then is I can get 5. Wait, let me write the sum. I'll still have this 5. If I distribute the n to the 3, I'll have 3 to the n, 3 to the n, that. And then when I distribute the n to the x to the 5th, I'll get x to the 5n. And if I multiply the x to the 5n with this x, I will get x to the 5n plus 1. Right, this is g of x. So if we want to take the derivative of that, since f of x equals the derivative of g of x, f of x is the derivative of the sum of, from n equals 0 to infinity, of 5 times 3 to the n times x to the 5n plus 1. And you're like, okay, cool, what do I do now? Well, you can just literally take the derivative of this, like you're just taking a derivative of a normal function. So the derivative of this, remember when you take a derivative, you take this exponent, you bring it down, and you subtract 1. You're literally going to do that exact thing. So f of x will just be the sum of 5 times 3 to the n, and we're literally just going to take this exponent, bring it down, so we'll get 5n plus 1 times x to the n. We'll subtract 1 from here to get us 5n, and that is our series for f of x. So, okay, that's fine. So now for the interval of convergence, we're going to use the ratio test. So we'll take the limit as n approaches infinity, and we'll look at the n plus 1th term divided by the nth term. Okay, so the n plus 1th term will have 5. So if I plug in n plus 1 here, I can use my laws of exponents to say that's equal to 3 times 3 to the n. And then for 5n plus 1, if I plug in n plus 1 here, I'll distribute the 5, and that'll give me 5n plus 7. No, not that. 5n plus 6. 5n plus 6. Okay, and then x to the 5n, that's going to give me x to the 5 times x to the 5n. Right, that's just, if I plug in n plus 1 here, I'll get 5n plus 5, which is this and this. Okay, so I'll divide this by the original one, the nth term, 5, 3 to the n, 5n plus 1, x to the 5n. So the reason I made the numerator look like this, instead of just leaving it as n plus 1, 5n plus 1, etc., is that now everything here is going to cancel. You'll see a lot of it is going to cancel. So this 5 here cancels, this 3 to the n cancels, this x to the 5n cancels. So we're left, oh, by the way, before I forget, let me leave the absolute values here. Okay. So once we do the simplifications, we're left with the limit as n approaches infinity of the absolute value of 3 times 5n plus 6 times x to the 5th over 5n plus 1. Okay. Okay, so now if we actually evaluate this limit, notice that we're going to be looking at the, if you were the, since this 5n here and then the 5n here, the exponents are equal, so we're just going to be looking at the coefficients. On this side we have 3 times 5 is 15, on this side we have 5, so the ratio of this is 15 to 5 is 3, and then we have this x to the 5th here, so this limit is equal to 15 over 5, which is 3 x to the 5th, and with the absolute value here. And then, remember, for the ratio test, this stuff here needs to be less than 1. So less than 1. And then if we, like, negative 1 is less than 3x to the 5th, is less than 1, divide both sides by 3, and then you can take the 5th root. It'll get you the 5th root of negative 1/3 is less than x, is less than the 5th root of positive 1/3. And then, yeah, so that is our interval of convergence right there. If we were to plug in the 5th root of negative 1/3 or the 5th root of positive 1/3 back into our series here, we find that we can combine this and this, and we'd get 1 to the n, or negative 1 to the n, which would be, again, a divergent geometric series. Okay, so this stuff here, actually, I realize now, we could have also done this using the geometric series argument, so both of those would work, but anyways, we chose this one, so this is our interval of convergence. Okay, so this last one here, f of x is equal to the natural log of 5 minus x, and we want the radius of convergence. I'll be honest, this one is very tricky. This is probably trickier than what you'll see on the AP exam, but I want to give you hard problems so that the AP exam seems easy. That is my style, if you haven't noticed already. So, we want to figure out the power series for this. What we're going to do now, actually, the way we're going to approach this problem is we're going to notice that if I were to take the integral of 1 over 5 minus x dx, this would be equal to the negative natural log of 5 minus x, which is equal to negative f of x. So f of x is equal to the negative integral of 1 over 5 minus x dx. That's the key insight here. So I'm going to just focus on this 1 over 5 minus x part, okay? So 1 over 5 minus x equals, I can factor out the 5 since I want to get into a 1 over 1 minus something. This will be 1 over 5 times 1 over 1 minus x over 5, like this, okay? So this is a very simple power series to do. This is just equal to the sum from n equals 0 to infinity of 1/5 times x over 5 to the n, right? I can rewrite this also as the sum from n equals 0 to infinity of x to the n over 5 to the n plus 1. Because I can distribute the n to the bottom here, and I'll get 5 to the n. And I'll combine that with this 5 to the 1. So 5 to the n times 5 to the 1 is 5 to the n plus 1, like that. So I'm going to use this version of the series. And since this is equal to 1 over 5 minus x, these things are equal. I can go in here and I can plug in this series for the 1 over 5 minus x. So f of x is equal to the negative integral of the sum from n equals 0 to infinity of x to the n over 5 to the n plus 1 dx. And remember, this entire thing here, this integral of the sum, this is just equal to the natural log of 5 minus x, remember? This entire thing is just to find the power series for ln 5 minus x. Okay, so what do we do now? We have the negative integral of the sum. What are we going to do from here? So I can actually, just like in the previous part where we took the derivative just like it was a normal thing, we're going to do the exact same thing here. We'll take the integral of this just like it's a normal thing by increasing the power by 1 and dividing by that power. So f of x will be equal to, so now when I actually do this thing, I'll get negative of, let's see, it's going to be the sum from n equals 0 to infinity of x to the n plus 1 over 5 to the n plus 1 times n plus 1, like that. And then, of course, it's also going to be a plus c. And just to get rid of these giant parentheses, I'll rewrite this where f of x equals c minus the sum. So I'm putting the c in front so I don't have to put these annoying parentheses. They look really ugly. 5 to the n plus 1 and n plus 1. Okay, we're good. So this is the power series, right? But notice we also have this plus c. So let's figure out the value of that plus c. How do you think we're going to figure out that value? Well, we'll just plug in some random number for x. Okay, so let's say plug in x equals 0. Let's do f of 0. That's going to be c minus sum from n equals 0 to infinity of 0 to the n plus 1. So 0 to the anything is 0, right? So this entire thing will be 0. So f of 0 equals c. Well, what is f of x? Remember, f of x is just the natural log of 5 minus x, right? So c is equal to the natural log of 5 minus 0, which is the natural log of 5. So c is equal to the natural log of 5. I can plug that back into here, and that'll give me my final power series representation for f of x. Our final answer is f of x equals our constant, which is the natural log of 5, minus the sum from n equals 0 to infinity of x to the n plus 1 over 5 to the n plus 1 times n plus 1, like that. That is our final answer. Like I said, this one is probably a bit more difficult than anything you might see on the AP, but it's good practice. So now looking at the radius of convergence for the series, looking at the x to the n plus 1 and the 5 to the n plus 1, I could rewrite this as x over 5 to the n plus 1. So I want this x over 5 thing to be in between -1 and 1. So -1 is less than x over 5 is less than 1. That means -5 is less than x is less than 5. And remember, if x is equal to -5 over 5, we'll get a common ratio of 1, which will cause a geometric divergent series. So since this is our interval of convergence, and we have that the center is at x equals 0, right? This naturally this is centered at x equals 0. That's going to mean that our radius of convergence is the distance from 0 to either 5 or -5. So the radius of convergence is 5, like that. Okay, that was the end of question number 3. Let's look at question number 4. Okay, so in question 4, we have f of x equals x to the 4th over 9 plus x squared. And in part A, we're asked to find a power series representation for the indefinite integral of f of x dx. Okay, so we want to find the power series for the indefinite integral of x to the 4th over 9 plus x squared. No, that's not how it looks. 9 plus x squared. So like in question 3, if you actually took the integral of this question, that was by far and away the worst way to go. We're just going to take the power series of this f of x, and we're going to integrate that power series. That's it's so much easier. So let's see what we can do. So this f of x, it looks kind of similar already to 1 over 1 minus x, right? All we got to do is we got to mess with it just a little bit. So first we'll take f of x, and we'll take this x to the 4th and we'll bring it out. So we'll get x to the 4th times 1 over 9 plus x squared. Okay, and notice here there's a 1, so to make this one, I'll pull out a 1/9. So we'll get x to the 4th over 9 times 1 over 1 plus x squared over 9, like that. Okay, and then finally, notice that it's 1 minus a thing. So now I have a plus here, so to turn that into a minus, all I'll do is I'll replace the positive with 2 different negatives. So 1 minus negative x squared over 9, like that, okay? So now we do have it in the form that I want it, 1 over 1 minus a thing, right? So now to put it in the power series form, it's going to be the sum of n equals 0 to infinity, and I will have this x to the 4th over 9 tagging along. So it's going to be right there, it's not going to go away. And then instead of x to the n, it's going to be negative x squared over 9 to the n. Okay, and now since we know that we're going to be taking the integral of this in a moment, to make the process as easy on ourselves as possible, we'll simplify this stuff here. So what I'll do first is I will expand the exponent here, and I'll bring the n into x squared into the 9 and to the negative here. So if I do that, I will get, so the negative and the n, that'll bring us a -1 to the n in the front. So we'll have the x to the 4th over 9, and then we'll have x to the 2n over 9 to the n. I can separate these if that's better. Okay, and then now how do we simplify this a bit more? Well, we have a 9 to the n here, we have a 9 here. I can combine those two to get 1 over 9 to the n plus 1. Actually, you know what I'm going to do instead of that, actually? I'm going to, since there's just a 1 up here, I can just replace this as 1 over 9, the entire thing to the n plus 1. And then I have an x to the 4th and x to the 2n. Combining those gives me x to the 2n plus 4. Okay, so we're not done. This was f of x, right? I want to take the integral of this power series. So I want to take the integral of this power series. While I rewrite the power series, think about how you're going to actually take this integral. Yeah, so basically, we're really going to treat this just like a number. We're going to increase it by 1 and divide by that number. So we'll get, and don't forget your constant c, by the way, so we'll have c plus the sum, and I'm putting the c at the beginning instead of at the end, because I don't want to put a giant parentheses around it. -1 to the n, 1/9 to the n plus 1, x to the 2n. So we're adding 1 to this, because it's an integral. So we'll get 2n plus 5, then we'll divide by the 2n plus 5. So we'll get 1 over 2n plus 5. And that is the power series for the integral of f of x, like so. Okay, so now let's look at the second part, part B. So now in part B, we need to estimate the integral from 0 to 1 of f of x dx to within 1.5 times 10 to the negative fifth. And to do this, we're going to use this power series that we generated in part A. Okay, so when we're going to estimate this, the first thing that we're going to do is we're going to basically list out a bunch of terms in this power series. So we'll start by plugging n equals 0, and n equals 1, and n equals 2, and so on. We'll just do a couple terms, and we'll see what happens. Okay, so first let's plug in n equals 0. Plug in n equals 0, we're going to get negative 1 to the 0, 1 over 9 to the 0 plus 1, so we'll have 1 over 9, 1 over 9, and then x to the 0 plus 5, so x to the fifth, and then 1 over 2 times 0 plus 5, so that's times 1 over 5. And then next, if we look at n equals 1, we'll have negative 1 to the 1, so we'll have a negative, and then 1 over 9 to the 1 plus 1, so 1 over 9 squared, and then x to the 2 times 1 plus 5, so x to the 7th, and then 1 over 2 times 1 plus 5 times 1 over 7. And then I can repeat this process. I'll do it 2 more times for no particular reason. Minus 1/9, okay, let's scoot over a bit. 1/9 to the 4, x to the 11, 1 over 11. Okay, so we've done this, right? Now let's see what we do now. So we want to estimate this to within 1.5 times 10 to the negative fifth. Okay, so what we're going to do is we're just going to look at what the actual value of these terms are if we were to plug in x equals 1, because we're taking the integral from 0 to 1, okay? So now we're going to plug in x equals 1 into each of these, and we're going to see where we're going to get. So if we plug in x equals 1 into here, we'll get 1/9 times 1/5, which if you put it in your calculator, you'll get 0.0222. And then the second term, if you plug this in your calculator, you will get 0.00176. And we're going to keep listing out the successive terms until we get a number that's less than 1.5 times 10 to the negative fifth. Okay, so then now we have this this third one here. If we plug in x equals 1, we will get 1.52 times 10 to the negative fourth. Okay, and then for this last one here, we'll get 1.39 times 10 to the negative fifth. And hold on a second, this was 1.5 times 10 to the negative fifth. So we've reached a number that's less than that. So we can stop. If this was greater than that, then we'd have to list the next term and so on and so forth. But we can stop here since this number is less than 1.5 times 10 to the negative fifth. So now that we've reached this threshold, what we'll do is we will ignore the last term. So we'll ignore the 10 to the fifth part, and we'll just look at these terms that came before it, and we'll sum those up. So we'll get 0.0222 minus this plus that. If you put that in your calculator, you will get 0.0206109696. Okay, so this is actually our approximation. So if we're going to list the steps that we did, we listed out the first few terms of the series. We found the actual values of it when we looked at the number that we wanted to take the integral to, and then we looked at where it went past the error that we wanted to find, and then we summed up all the terms that came before it, and that gave us our actual estimation. Now, if you're curious, the actual value of the integral from 0 to 1 is 0.020598302. So we were pretty close. We were a very, very small amount away, so we did pretty good. We did well. Okay, so that was the end of question 4. Let's move on to the fifth one. Let f of x be a function having derivatives of all orders at all real numbers. The third degree Taylor polynomial for f of x about x equals -2 is given by what is shown. Additionally, it is known that the absolute value of the fourth derivative of x is less than or equal to 25 for -2 is less than or equal to x is less than or equal to 0. Find the Lagrange error bound for the approximation to f of -1.6. Cool, let's do this. So the Lagrange error bound, the formula for that is as follows. So it is less than or equal to the absolute value of the n plus 1th derivative at some constant c divided by n plus 1 factorial times x minus a to the n plus 1. I'll explain all this in a second. So n is the degree of the polynomial. In this case, we have a third degree to polynomial, so n equals 3. X is where we're taking the polynomial at, the x value, and since we want to find it at negative 1.6, x equals negative 1.6. A is where the polynomial is centered. The Taylor polynomial or the Maclaurin polynomial is centered. In this case, since we have a Taylor polynomial centered at x equals negative 2, we have a equals negative 2. And then f, the n plus 1th derivative at c, this is the maximum of the n plus 1th derivative. So since we have n equals 3, this is the maximum of the 4th derivative. So in our case, it is known that the 4th derivative of x is less than or equal to 25. So the maximum of the 4th derivative is 25. So f for c is 25. The absolute values don't really matter because here we have absolute values as well. Okay, so with these 4 bits of information, it's really as simple as plugging it into the function. So negative 1.6 is less than or equal to, let's see, so this is 25. This is 4 factorial. This is x is, what is x? X is negative 1.6 minus, and then a is negative 2. And we're raising this to the n plus 1th power. Right? So 25 over 5 factorial times that. So let's simplify this a little bit. 4 factorial is 24. Negative 1.6 minus negative 2 is positive 0.4. Bad. So we take this, put it in our calculator, we will get that the remainder is less than or equal to 2 over, no, that's still on eraser, hold up. 2 over 75, there we go. Okay, that was a really simple question about the Lagrange error bound. Notice that we didn't even look at the function at all. That was completely extraneous. Anyway, so we're done with question 5. Let's move on to the final 6th question. Final question. Let f of x equal cosine of 2x plus pi over 6. Okay? And that p sub 3 of x be the 3rd degree Maclaurin polynomial for f. That's key. Maclaurin polynomial, remember that means it is centered at x equals 0. So now we want to use the Lagrange error bound to show that the absolute value of f of 1/3 minus p sub 3 of 1/3 is less than 1 over 100. So this kind of format is something you might see on the AP, and the thing that you should remember is that whenever they show you this kind of thing, that the first thing your mind should go to is they want me to use the Lagrange error bound formula. This kind of f of 1/3 minus p, that's like pretty much a giveaway that they want you to use Lagrange error. So just remember this. First, let me write down the formula for Lagrange error. So I'll write down the general formula first. So if we want to find the error at some number n of x, this is not equal to, that's the wrong way. So it is less than or equal to the absolute value of the n plus 1th derivative at c, where c is some number, divided by n plus 1 factorial times x minus a to the n plus 1. So what is this formula here? F n plus 1th derivative, this is the maximum of the n plus 1th derivative. This is n plus 1 factorial, easy enough. X is the x value, a is the center, n plus 1 is n plus 1. So in our case, let's see what we already know. We know that n equals 3 because we're looking at the third degree polynomial. So n equals 3. We know x equals 1/3 because we're dealing with the polynomial at 1/3. Not n again, it's x. X equal 1/3. Then since this is a Maclaurin polynomial, we're centered at x equals 0. So a equals 0. Okay, and then let's look at the n plus 1 at c part. So since f of x equals cosine of 2x plus 5 over 6, if we were to take the n plus 1th derivative, since n equals 3, we're going to be taking the 4th derivative, right? So we're looking at the 4th derivative of x. If I were to take successive derivatives of this, by the power rule, I'm going to get 2 times a trig thing, and then if I take the second derivative, I'll get 4 times another trig thing, and if I were to take the third derivative, I'll get 8 times a trig thing, and if I were to take the fourth derivative, I'll get 16 times a trig thing, right? So this is going to be 16 times a trig thing. And by trig thing, I mean a sine or a cosine or a negative or something like that, right? So for whenever you're dealing with these trig things, as I like to say, the maximum value for those are always 1, right? For sine and cosine, the maximum they can be is 1. So this is 1, this is 16, or the maximum of this is 1, this is 16. So the maximum of f, the fourth derivative of x, is 16 times 1, which is 16. So f for c is 16. This is the maximum, right? It can never be more than 16, because you'll never be able to multiply 16 by anything that's more than 1, because this can be at most 1. Okay, so we know that we have this, so we can just plug everything into our formula now, and we will have our answer. Okay, let me just erase this. Okay, so let's plug in our formula. So the third degree remainder at 1/3 is less than or equal to the absolute value. So we said, okay, this is 16, right? That is a fact. And we're dividing by n plus 1, so it's going to be 4 factorial. And then we're multiplying by x is 1/3, a is 0, so it's 1/3 to the n plus 1 is 3 plus 1 is 4, so it's the 4th power. And if we were to put this in the calculator, you would get that this is less than or equal to 2 over 243, right? And we want to show that 2 over 243 is less than 1 over 100. Well, it's obviously less than 1 over 100, right? This is 2 over 200, this is 2 over 243, this is obviously smaller. So this allows us to conclude that the remainder at 1/3 is less than 1 over 100. We've proved what they wanted us to prove by using the Lagrange error bound. Okay, that was it for this video of series in AP Calculus. We're done with the series unit, and yeah, moving on. I will see you next time. Goodbye.